It's not raining, so I assume there's an assignment due or exam. No, not more open seats today. Any questions? Well, so we were talking about linear regression last time. We're basically, we have a data set and we want to plot a line that approximates the data, right? But of course, it doesn't matter what the data is. We can always do regression on it, right? And get the regression line. It doesn't mean that line presents anything valid, right? It depends on what the underlying process that generates the data is. A lot of processes are linear, but not all processes are linear, right? So we have a process which is quadratic or logarithmic or exponential, right? And so doing a linear regression to it is going to come up with a bad fit. But if we know what the underlying process is, we could probably then, we don't need linear regression because we can just, we know it's linear, and so we can start trying to, experimentally produce the exponents we need, or A and B, the equation, and just solve it. And you don't need to do all this stuff, right? But usually we're doing this because we don't know exactly what the underlying process is. So a couple of things we can do to try and help at least validate somewhat whether it's a good way of doing it, right? One is residuals, another is this famous number R squared. And like residuals, well, here's our data. And the residual is just, you take the actual value you got and the projected value, right? And you subtract them, and that's your residual. And if indeed the process is a linear one, you'd expect then that when we fit the data with a linear line, approximately half the data will be above the line, half the data will be below the line, and if enough data, it shall average out, right? So that means several things. One is you expect residuals to be randomly distributed. There shouldn't be any pattern to it, and you expect the sum to be close to zero and the mean close to zero. And when I did that here with our data set, we get this plot, right? And there's zero. So some values get down to -2. We don't have any values at +2, but they're pretty close, right? So it gives us a fairly good feeling that, this really is, right, a linear process. And I get this one. No, not that one. That one. So R squared, we've got this nice equation where it's the variance of the residuals over the variance of the observed data. Subtract that from 1. And since variance is always positive, right, the R squared is always going to be 1 or less. And the closer it is to 1, the better. And so here, when I compute our R2 score from our data, we get 0.97, which is another indication that it's a good fit. It's a physical match, not a we haven't discovered some underlying process and proved that it's linear, but we have a physical test which they can fail us, and they do at times. And yeah, if it's only one independent variable, it reduces down to Pearson's correlation squared. And now we can finally understand this comic a little better. R squared equals 0.06. R squared for two-dimensional graph should be between 0 and 1. And if it's 0, it means just forget it. I mean, it's completely random. And so this is a pretty bad. That was just regression with one independent variable and one dependent variable, right? But one of the things we talked about, one way I'm motivated is, look, we want to determine the factors that determine how much money Amazon makes per day. There's a bunch of factors, so all these become independent variables. And so how do we do multiple linear regression? Simple example again. So let's do this, right? I have two independent variables, x and z. And then to fake data, what I'm doing is I'm computing that value and then adding some random noise to it. Now the problem is now we got three-dimensional data, right? And as soon as you get three-dimensional data, it becomes harder to visualize. And so here is the scatter plot plotting x and y, but the z we forgot about, right? The data, and when you do it z and y, it looks a little better, but again, we're just projecting down, and so it's hard to see what's really going on. In a little bit, we'll look at an example where we're talking not just two independent variables, we're talking thousands of independent variables. So usually using these libraries, once you get down to actually doing it, it's pretty simple. It's processing all the data and then figuring out what you actually did, right? Import linear regression, and then I just call fit on it, and I give it the data where I say, okay, we need to give it two things. We need to give it the features or the independent variables, and then the dependent variable results, right? And so I create a data frame, and so I could combine them together easily, x and y. And then I can start, once I fit it, I can ask the model, what are your coefficients of x and z, and then the intercept. When x and z are 0, what's that constant? There we go, right? And so then our model becomes this. And remember, we were modeling that, right? So the coefficient is not very good, right? It should be -1 and it's 0.3. 2.9, that's pretty good. That's 3, and then the 2 is 1.86. That's not as good as it was before. But it's basically the same process, right? Then we can look at the residuals. The mean is pretty close to 0. The sum is not so great, right? And now looking at the residuals become hard because again, we've got three-dimensional data. So I did it in computed the z and the x, and it doesn't look too bad, right? It's sort of random. So one problem is we have a three-dimensional space, and so it's bigger, and so the points can be farther apart. And so when I did 50 data point, which I did the two-dimensional one, the results weren't as good. When I did it with 100 data points, we started getting more accurate, and then finally, with 1,000 data points, we're getting better results. This means if you got n-dimensional data, you may need more data to. And then your R squared gets slightly crazy because the more features you add, the more variables you add, that increases the value of R squared. And there's a way of compensating for that, but I couldn't find a computation in Scikit Learn that did that, so I don't. So far, so good. So I'm looking at a little bit by Scikit Learn, and then a little bit on Bayes, and using Bayes results. Scikit Learn is a pretty popular machine learning library in Python. It comes with the Anaconda installation of Jupyter notebooks. And the basic operation is pretty simple. You choose which model you want to use, then regression or Bayes or clustering, k-means, whatever. Hyperparameters are just parameters that you can set on the model. And then we need to create our feature matrix. Basically, a matrix of all independent variables, and your target vector, which is your dependent values. You then call fit on the model with that information, and once you've done that, we can now apply the model to new data to get our predictions. Right? It's pretty much the same process over and over again. Though it may take a while to actually get the data in the right format, etc. And yeah, that process is pretty similar to the way you do it in Julia. It's going to be similar to the way you do it in Spark. So what they call a feature matrix is this basically, right? Your data points for each feature, right? In a two-dimensional matrix. And then your target vector is, right, the value you measured from your data on the dependent variable. All right, so a previous example, here's my target vector, the y values, and then I create a two-dimensional matrix out of the x values. And that's your featured matrix, and then I call fit on it, and then I can call keyword values of x and call predict on that, and I get new values of y. Same process over and over again. And Scikit Learn has a bunch of models, a bunch of functions, and so the documentation, it could be better, but it's been around a long time, so you can probably find someone who's done an example of what you want. Now, another way of modeling things is using Bayes' theorem, and it's fairly popular. So some definitions, right? P of A just means the probability of A, and then same for B. And then P A slash B means what's the probability that A is true given that B happened, right? And then probability B slash A is the reverse. And Bayes' theorem says like the probability of A given that B happened can be computed by the probability of B slash A times the probability of A divided by probability of B. And the whole point is hopefully we know probability of B, probability of A, and probability of B given A, and that allows us to compute that, right? And here's my simple example where, counting the number of people in a school, number of teachers, number of students by sex. And so if you want, can we compute the probability that someone's a teacher knowing that they're male? Well, from the table, we can do that pretty easily, right? Using Bayes' theorem, well, we can compute these values, and then, we can use Bayes' theorem, and then we can substitute those values in, and then we start, simplifying things, right? To the left further, and then we get that, and then finally we get, and indeed that makes sense because if we know they're males, there's 60 males, and out of the 60 males, 12 are instructors, right? And there's a whole branch of physics that is based upon Bayes' theorem. And if you're Bayesian, then it's a big deal. And so we're going to use Bayes' theorems to do classification. And the idea of classification is pretty simple. You have some data you've got to review, and you want to classify this review as positive, negative, or neutral. And so what you do is you gather a bunch of data, get a bunch of reviews, and then you hire some undergraduates, read them all, and classify them as positive, negative, or neutral, right? And then, we want to be able to take a new review and use that existing data to say, oh, this should be a positive or negative or neutral review. Well, so we can use Bayesian to do this classification, and the problem is, so here's our Bayesian theorem, and then we substitute in A, B, the label we want to know about, and the probability of a given features occurred, and then it's like, okay, probability of features given a label times the probability of a given label, and then the probability that feature occurs. The problem is we probably don't know what the probability of those features occurring are because we just have a sample. But if you get two labels, we can divide one by the other, and that gives us just, given label 1, what's the probability of those features occurring, times the probability of label 1, and same thing. given our data set, we can say, okay, what's the probability of a given feature given that it's label 1? Well, that we can compute from our data. We can also compute the probability of a label 1 occurring because we have our data. We can use that estimate. And so we can use this equation to start using Bayes' theorem based on our data. Of course, it's all done for us, right? We're just going to a function called fit. So one process is called Gaussian naive Bayes, and it's called naive because we're making an assumption about the underlying distribution that's happening. So I'll do 2 examples. First one, fake. And the second one, we'll use actual data. So the fake information, okay. So I need 2 groups. And so Scikit Learn has this thing called make blobs. It creates data sets that are in groups. And so we want 100 items. We want 2 groups, 2 separate centers. So that each group has different centers. So there's some separation. And then the standard deviation of all the elements in each group will be 1.5 from the center. And then we get several things. One is we get X, which is our feature matrix. So it's our independent variables. And then the Y is our dependent variable, which category it's in, the first blob or the second blob. And since there's only 2 blobs, we can then plot so here's our data. And so we've got 2 separate groups, one red, one blue. And so our goal is now to use, given other data, right? How can we use Bayes to actually determine which group it's going to be in? The red or the blue? Yeah, so the Y vector is just an array of zeros and ones, which group it's in. And then our feature matrix is just a set of coordinates in a 2-dimensional space because there's 2 blobs on 2 dimensions. And this is all the parameters we have for making blobs. Scikit Learn has a number of functions you can call to generate fake data, so you can try it out. First, well, so now we've got our 2 fake data, our data. We want to then train a Gaussian model, so we can then pick off points and see where they belong, right? Which group they belong into. And so we'll use a Gaussian, and then we just call fit on it. And then, I want to create some test data so we can then see where it goes. So I'm creating 2,000 random numbers between 0 and 1. And I want pairs of them. So I need x and y coordinates. And then what I do is multiply by 14 and 18. So now the x coordinate goes from 0 to 14, and the y coordinate goes from 0 to 18. And then we add, right, that pair to it. So now the x coordinates go from -6 to +8. Did my arithmetic right? 6 plus 8 is 14, right? And then the y coordinates go from -14 to +4. Yes, that's sort of nice, right? I mean, in Java, you're dividing all these for loops, and it's like, no, I get that. I mean, and so here's this explanation, right? You know, the random computes pairs, and here's an example of the pairs. And then here's an example of the result. Right, and that's the range we're going to get. Now we want to predict, right? You know, where are those points going to go? So we just call predict on the model, given our, our coordinates, our features, and we get the prediction, and then we get this complicated thing. So what's going on here? I want to do a scatter plot of the x, the x and y the two coordinates of our independent variables. I want colors. And this C map is a coloring scheme so we can see it. And then I do another scatter plot of the new values. But the colors now are going to be based upon the values of our prediction. And so I get this crazy graph. You know, the dark blue are the original data set, the dark red, but the light red and light blue are the plots of all the data we predict. We created an X new, and we're using the Y new to determine whether it should be red or blue. Right, so it's showing you, right, there's basically a line here that divides one set from the other. And so anything below this line, the model will say it belongs to this set, and everything above it, other set, right? Yeah, and the Y new is just a bunch of zeros and ones. So the naive Bayes processes they're usually very fast, and it's a pretty simplistic model, so we can understand what's going on, and you don't have to worry about all these parameters you can tweak and twiddle. We'll see another algorithm with a bunch of parameters you can tweak, and tweaking them gives you different results, and then you have to figure out which one to use, and is that a good thing or a bad thing? And yeah, there are advantages to it when to use it. So now I want to use the same process to analyze text, right? And so the example we're going to use is there. Oh, let's see. Does anyone remember news groups? You know, before the World Wide Web came out, there was internet news groups, and you subscribe to the news group, and people would post questions, and there'd be big arguments, and they discuss things. And so we're going to look at some news groups, and of course, the news groups. I mean, you had a group on every conceivable topic, right? So we'll pick news groups and different news groups have different topics, and then those will be our data sets, and then we will, from those data, we'll pick some testing data, right? We'll divide it into training data and testing data. We'll then train the model, and then we'll use the test data to see how and make predictions of what group that really is in. But how do we actually do that with words, right? So let's assume that our vocabulary only has 5 words in it, right? And those are the 5 words we know about. We want to convert those words into vectors. And once they become vectors, then it becomes, you know, we had vectors in the previous case, right? It was just it was only X and Y, but they were vectors. So how do I convert those words into vectors? So let's say I have the sentence, bad at dog. And what we do is we order, right? We fix an order of our words, in this case, alphabetical. And that then, our vector is going to have 1 dimension for every possible word we have. And so the first element is going to say, if it's 0, it means that sentence did not have the word. Yeah, so it's wrong. It should be 1001, right? Yeah, it should be 111. Very good, right? You're awake. That one's correct, right? And what if someone does this, right? Well, sad isn't in our dictionary, right? So ignore it. So we can convert these things. We can convert all our words into vectors, right? And once they're in vectors, we can just forget that they were words, right? And do the same process. So then the game plan is, okay, I'm going to take all these news groups, all these, you know, messages from the news groups, and then you go through them all and you find out every unique word that's in the list, right? And that becomes our dictionary or our list of words. And once we've done that, we can then go into each message and then count how many times each of those words occurs, and then create a vector for, and each one of those messages become a vector, right? And then once I've done that to all the messages in my training data, I can pick a new message, right? Convert it to the vector using the same technique, and then just ask, the model, which group they belong in. So we have to take our text messages, right, and break them into words, and then we convert each word into, token, and then we count how many tokens occur in each document. And we also may need to put some weights on it, depending upon what we're interested in. Some example is, we want to know whether it's a good review or bad review. But the problem is, there's some words which really don't tell us much about whether it's a positive review or negative review, right? The word "the," it's everywhere, and so forget about it, right? Just throw it away. You also may want to drop punctuation, right? Because that really, I guess if there's lots of exclamation points, then you might consider that you guys sort of upset, right? So you may want to drop punctuation, and then we get all kinds of things. What do we do about these words which are variants of the same word, right? Laughing, laughed, laugh. Should we count them as the same word, or should we count them as 3 different words? So some systems will actually allow you to take, they have a huge dictionary, right? And there's various algorithms to try and determine what is the root word of a individual word, right? And there's a bunch of other processing we can do to process our text. And then we can order the remaining words, and we can then use it to vectorize, right, each of our reviews. And we need, of course, words to confuse outsiders, so that it sounds like we know something. These are called stop words. Why? I don't know. Then, each review, I find all the reviews which are positive, and I convert them all into vectors, and that becomes our set of vectors that we use for our data, right? And so we can mark them. Here's our 5,000 positive reviews. Here's our 3,000 negative reviews, and here's our 200 neutral views, right? And then we can create the vector for each one, right? And then we mark them as positive, and then we put them into our feature matrix, right? And then the Y matrix becomes whether it's positive, negative, or neutral. And then we feed into the Bayes algorithm, and then we can call fit for or predict to when we get a new review. Of course, you have to be careful, because if you've got 5,000 reviews and we start looking at the number of unique words in 5,000 reviews, it's probably a lot, right? And remember, each word we keep becomes a dimension in our vector. So we could have, we're no longer talking about a 3 or 4 dimensional space. We're talking about, thousands of dimensions. So it's a good thing Bayes is fast and works well with high dimensions, right? And so, but the problem is, right, a particular sentence or particular review probably doesn't have, it's not going to have all the words in it. It's going to only have a few of the words. And so when you create this, 3,000 dimensional matrix, there's only be a few ones in it. And if you've got lots and lots of reviews, that takes a lot of space. And so we want a sparse representation of that, right? It'll probably be more space efficient, just list the locations in that vector where it has ones, right? And Scikit, when we do this in Scikit, it automatically uses a sparse representation for us. Even when you look at it, it looks like it's a full matrix. No, they're being space efficient for us. But this is something to be aware of when you're dealing with large data sets, right? Can we represent it in a smaller space? So Scikit has a number of ways of doing this. There is a count vectorizer. You give it a text, a string, and it will then convert that into a matrix of token counts, right? How many times each word occurs. You have your transformer. Well, it actually takes the output of the count vectorizer and does some normalizing on it. We'll talk about that a little bit later. And the vectorizer is basically a shortcut for first calling the count vectorizer and then the transformer. And these functions, they will tokenize. So you just give it the string, right? And it'll tokenize it for you. It removes stop words. It drops punctuation. It doesn't convert to words, right? It doesn't. If you've got a plural in there, it keeps it there. If you've got laughed and laughing, it keeps them as separate words. So if you really want to do that, you have to do some more work, and it's hard work. And I was surprised not to see it in Scikit Learn because there are routines out there which do that based upon a data set in English. So the fact that there wasn't in Scikit is like, why don't you have that? And then it'll spit out a vector for each document. Now this TF-IDF transformer, the TF stands for term frequency. And you'll see it abbreviated as TF, comma, T and D. And the T stands for a particular term, and the D stands for a single document. There are lots of ways of doing this. One is just raw count. How many times that term appear in a document? Right, straightforward. Boolean, it's either 0 or 1. It's in there or not in there. Length adjusted, well, it's just the raw count divided by total number of words in the document. Another typo, but another one is taking the logarithm of that value. So there's lots of different ways of doing this. People have been trying to tweak it to figure out, how can they get the best results. And there's no really good theory to explain all the ways they try and tweak it. The IDF, inverse document frequency. The goal is to try and measure how much information that word provides, right? And if the word is in every document, it's not going to help us separate the documents out, right? Because it's everywhere. So it doesn't give us information. If a word only occurs in one document, it's extremely rare. It's not going to be very useful either because it's so rare that we hardly ever come across it. So they want a way of actually making extremely common words count less and extremely rare words count less. And that's why they call it inverse document frequency, because you expect a word that's in every document to have a high count, but we want to have a low count, right? And there's, again, all kinds of ways of computing it. And then the TF-ID is like the two multiplied together. And again, the goal is pretty much, if a word occurs a lot in a single document, then it should have a higher score. And if a term doesn't occur in many documents in the corpus, right? And a term appears in every document. It gets called every document, then that value should get smaller. So, simple example where corpus is just basically the set of documents you know about, right? And so here's each sentence is going to be one of my documents, and then I create a count vectorizer, and then I call fit transform on it, and then it's counted all the words and knows the frequencies and all, and here is a list of all the words that it found. And it converted each one of these sentences into a vector. And we can look at the vector. And since I didn't do it by hand, it should be right, right? Let's see, it says one is a document. Yes, is a document. The next one is first. There's a first. Next one is, there's an is. And then, one, no, there's no one there. There's no second there. There is a the, and there is no third, and there's a this, right? And we can actually, given a word, we can actually do things like tell me its number, right? So I could have just taken this whole thing and then use it, get vocabulary to tell me what transform it into the actual words were. And then we can start doing things like, take a new document and vectorize it for us. And since there's none of the textures in the corpus, then we get vector zeros. And there's a bunch of things we can do on count vectorizer. So far, so good. Do the same thing with a TF-IDF vectorizer. The same corpus, we transform it. We get it. Well, I didn't print out the result. I forgot to do that. And then try and see what's going on rather than doing the zeros and ones. And what I did was I created a data frame out of it, so I print out a nice chart, right? And so the data is going to be the contents of our feature array, and then the columns are going to be instead of just the words, right? And then it's showing you, right, the weight it gives to each those words in that particular document. And one thing to note is, let's see, now we can look at this, right? This occurs in 3 of the, but the weight this gets in each sentence is different. It's not the same. Well, these two are the same, right? And I'm not sure why that one's different, but the weights will vary. Right. Right, that's why it's 0, right? But why are these two weights different? Right? Oh, but remember, all we're doing is we're just taking all these words, right? And we're then putting a vector, and then we're not computing where the word is in the, or what other words, or it's all a mathematical formula. But yeah, I don't know. Now, sometimes, actually frequently, just doing a word count isn't enough. And so they will then use n-grams. So an n-gram basically is, look at all word pairs in the order they occur, right? Or triplets, etc. And so here's an example of actually computing, here I want individual words, pairs of words, and triplets as they occur, right? And then I'm doing it on this sentence, and I'm getting by and grams. I'm getting all the individual words, and then I'm getting, right, the pairs as they occur, and then all the triplets as they occur. So here's a real example. Well, it's a real example based on real data, but it's been studied over and over again. So Scikit Learn has a bunch of data sets you can download. And so there's one called 20 news groups, which is just basically a collection of articles from 20 different news groups. And you can get it, and then, here's a partial list of the various news groups they look at. And then here's looking at a, sample article and news group, right? Right, and so you get the headers, then you get the content, and you get the guy who sent it. And I have no idea how or why they're allowed to publish that data. It probably happened before people got worried about privacy and all that sort of stuff, but the person's name and their email address. It also could be that since they posted it on a public forum that's accessible by everyone, that they got by with it. But so let's do it, right? So we can select categories and only download those news groups to make it faster. And it's also smart enough to give us a training set and a test set so that they're just joint, right? We'll pick a random sample in these categories for the train, another random sample. They take a random sample and they divide it in pieces, right? This becomes training and this becomes test. And each time each one we get, there's the data, which means a list of all the articles. There's a description, and if you call print on it, it tells you about the data, and it goes on for pages and tells you how you can analyze it, and on and on and on. And then there's the file names. It basically downloads it to a file on your machine and tells you what those files are. And then we get target and target names. So the target names, well, this is a target, target shape. So the target is just basically what group they're in, right? And it's indexing the target names. Then to see the actual data, what I did is I convert it into a data frame. And so I take the data and I combine it with the target, and so I can see what group it belongs to, and then contains the actual message. One of the things I find is that you got all this data, right, and you're playing with it, and it's like, what did I just do, right? What can I do with it? And it's hard to see because you got hundreds of thousands of messages, right? There's like, so now I want to actually, convert each message into a vector, right? And then we have mark it with the actual group it's in, and then we can use that to train the model. And since that's done a lot, all these systems have a way of creating some sort of pipeline where they say, first do this, then do that, right? And so the pipeline says, okay, first I'm going to give you all those documents. First, transform the documents into vectors by using the vectorizer, and then when you're done, you can pass all that stuff into the in this case we need a multinomial DB, the Gaussian, because instead of just having two, we have multiple categories, right? One for each news group, right? And so the pipeline can have a series of transformations, and then at the end it has to have what they call an estimator, which means it has a fit function, which will spit out a model. And so training the model is just that. We need the data and we need the targets. And then we can train, you know, we can then, once we get the model, we can use the model to say, predict where we're at, right? And then it's like, okay, what did I just get out of it? Because, so labels is just an array of which group they thought it was going to be in. That's it. But then you have to figure out, if you really want to know which group that is, then we need to get the target names and then index into it and get the actual name out. And we can actually then take my test data and combine it with labels of the separate column. And then we can see, oh, here's all my test articles and what group it belonged in, right? So now you should be good enough to figure out how to transform all those numbers into the actual group names, right? People are nodding their heads yes, but that's only because you haven't thought about it, right? And here is, I'm looking at the second article. Second article, but the first one is too long. And they're talking about Adobe Type Manager. And let's see, that was so it was group number 0. So what was group 0 again? Graphics. Ah, right. It was talking about Adobe Type Manager, which is using, it's fonts, right? And so, yeah, it makes sense that talking about fonts would belong to a graphics. It's like, okay, how do we know just because that second article was right? What about the other thousands? Yeah, there's 1,423. Like, do you want to check them by hand? No. So here's one way to check it. Okay, I have no idea why they call it the confusion matrix. The confusion matrix, some people call it the error matrix. Basically, what we're doing is we want a matrix where, so what we're doing down here is these are the true labels, right? So we're saying, okay, computer graphics, how many articles in computer graphics did we classify as talk, religion, miscellaneous? Well, 0, right? Yeah, there's probably not much overlap between computer graphics and religion talk, right? But there were 32 graphics articles that we classified as being religion Christian. There were 13 articles that were actually computer graphics that we classified as space. And then there was 344 computer graphics articles that we classified as computer graphics. That's the confusion matrix. And then we do it, for each group. So why is it called a confusion matrix? I have no idea. Do you know? What's that? I guess. I like the error matrix, isn't it? Oh, right. But then to plot this graph out, I use the heat map. And heat map just colors them differently based upon their values, right? So these are all dark because they're all small, and these are, and the higher numbers they get, the lighter they got. And so, but then this is sort of in between, so it's different color. And to be honest, if you didn't come across examples of using, right, the heat map, it'd probably take you a while to figure out what parameters you want to use. And so my reaction is, well, that's not bad, right? So I got most articles right, but there's some I didn't get right. And then I'm going to go, well, can we look at some of the articles we got wrong, right? Just to see why. Yeah, so the test data is just the actual data that we use for tests. It's actually the articles. The test target is actually the correct classification that, you know, some undergraduate had to go through and mark them. Like we didn't do that because they were internet data for us, right? You post them to the right art, and then labels.data is the actual predicted values, right? And so I just created a data frame, right? So test data is the data column. Actual is the test target, and then, you know, predicted is all the labels. And of course, they're all these things are done by position, right? So they all line up. So now we can start looking at places where they don't match, right? And so then I can use the various ways of manipulating data frames. So here's my data frame, and then let's look at all the places where the actual result was 0, which was graphics, and the predicted result was 2, which was the religious Christian, all right. And now we get all the examples of where they were wrong, and then we can start looking at what they look like. And remember, yeah, that 0 is graphics, and 2 is social, religion, Christian. And then here is an example of one of them. And remember, it's about graphics, right? But it was classified as religion. My guess is, yeah, like, oh, make up your mind. You start getting my personal opinion. Right? That, but it becomes hard, right? Because remember, we decompose this into a vector, and so we need to know what types of vectors characterize, you know, the religious Christian versus what vectors characterize graphics why this one got characterized. Since those vectors are huge, it'll take some effort to XV. Right. Yeah, and then we can start trying to tweak our algorithm to improve the classification. So now you could, download a bunch of reviews from Yelp and enslave some undergraduate to actually classify them, and then you can use them to create a model, and then start predicting when someone has a new review. And then you can write a program to erase the negative reviews, and then go to local companies, and for a small fee, you will delete all their negative reviews, right? All right, we're done for the day.